Excuse me. Okay, so this talk, it's been retitled the Conditional Particle Filter, but actually it's, I'm going to touch on a lot of background, in essence, you know, how these ideas came about, and my personal, the stuff I've done that has led to the most recent stuff that we've archived a few months ago. And the most recent stuff is jointly with Anthony Lee and Marty Vihola. And there's older work with Eric and Frederick Linston, and there's some stuff with Nicolas Chopin and a PhD student of mine. Okay, so let's move on. Okay, so, all right, this is the best angle for me to stand so that I can see the board. Okay, so here's a running example. I'll be dealing with state space, with a state space model. And this is an example from you and Ming, 2011, but actually it's just a numerical example which I took from an earlier paper with Nicolas Chopin. Okay, so what I mean, so this is a hidden Markov model or a state space model. You've got a hidden process X. So X here is a real valued stochastic process. It evolves according to the AR1 scheme. So its new value at time t plus 1 is equals to rho times its old value plus additive noise, okay? And the additive noise is Gaussian 0, 1. Its variance is being scaled by sigma. Now, X is unobserved. What we observe is Y. And the observations are actually a discrete random variable. It's a Poisson random variable in this example. And the value of the observation is drawn from a Poisson random variable with some base rate mu, and it's been modulated by the instantaneous value of X at time t. Okay. So generally what I will do in this talk is I will denote random variables with capital letters. There are specific instances with small letters. And if there is a departure from this convention, then it's typically a typo. Okay? So in general, if you're not particularly interested in this AR Poisson modulated AR model, then we're interested in a system as follows. We've got an X process that is Markovian, and it does what it does irrespective of what Y is. Okay? And the X process evolves according to a transition probability density, and we've denoted it by, so the new value xt is drawn from a density f subscript theta. It's indexed by its old value, and it's a density in the second variable, little xt, and that's just whatever your dominating measure is, Lebesgue, why not? And then once you've generated xt, then you generate yt. That's the observation. It only depends on the value of x at that time. And that's drawn from this density, which is indexed by the current value of x as well. And these components theta in the densities represent the parameters of the model we are trying to infer. And that's the evolution of the random variables we're interested in. So what we'll be doing in this talk is we're interested in inference about the hidden process x. Okay? So here's the inference objective, for instance. This could be an objective. In the previous example, there are three unknowns. It is the AR coefficient rho, the noise that drives the AR process, and the base rate of the Poisson count random variable. Okay, so it's rho, sigma, and mu. There are three unknowns. And we'll lump them together, and I call it theta. And we are given a length of a time series from time 0 to capital T, and capital T in this talk can be very long, maybe thousands, hundreds of thousands. We're interested in sampling from this posterior distribution of theta and x0 to t. And an old favorite is the Gibbs Sampler. Okay, so a Gibbs Sampler, say one cycle of it. So let's just say I have a sample of theta and x from this posterior density or this distribution. You advance it to the next sample, theta dash and x dash. Okay, the dots or dashes represent advancement of the sample using a simple scheme like that. So you cycle through the variables one at a time. And for this specific example, okay, when we try to advance the parameters theta, it can be done in closed form. So the third component of theta is sigma. You can advance it in closed form, conditional on the values of x and the other components of theta, which is mu and rho. It's a gamma distribution with some parameters. And then once you have advanced sigma, I've denoted it in red. So sigma has been advanced, so sigma dash, and then you advance rho to rho dash, and that has a closed form distribution. And that's been advanced, and so now we advance mu to mu dash. And that's normal. And then the fourth step here would be to try to advance the state sample. And that should be advanced from the conditional distribution of the state process given the observations and theta. And that is something that you can't do in general. And in fact, for all but uninteresting cases, you can't do it. So in general, you can't sample from this. So you could think of an old remedy. An old remedy would be, why not just advance the state samples one at a time? So why not I cycle through component 0, 1, so on and so forth. And in which case, when I'll be updating component I, I've updated component 0 to I minus 1, and you could sample from the conditional distribution of component I given the components you have advanced, the ones you haven't advanced, and the theta you have advanced. And obviously, you don't know what the distribution of this is, so you can do Metropolis-Hastings move to accept or reject a proposal to advance xi to xi dash. Okay, but this won't work because there's too much correlation in the hidden chain. So, so what I'm going to talk about today is something called the conditional particle filter. And the final set, the new bit in this work, in this presentation, it comes at the end, is to do with an algorithm called the coupled conditional particle filter. Okay? But en route to that, I'm just going to say a thing or two about particle filtering. Okay, so particle filtering has been around for a very, very long time. I guess popularized by Gordon, Salmon, and Smith in 1993. Okay, and that's 25 years ago now. It's a sequential importance sampling technique to generate samples from the distribution of the hidden states given all the observations and parameters that define the statistical model. And it's an importance sampling technique. In particular, it's sequential, so you generate the samples of hidden states sequentially. So given that it's importance sampling, it's you're going to have some weights to correct for the discrepancy between your proposal distribution in an importance sampling and the actual and the target distribution. So here, this just says that if you want to compute the expectation of some function of interest h, computed across the trajectories of the hidden state, the conditional expectation of this guy, given the parameter theta and the observations you've seen, you can approximate this with this sum with this importance sampling estimate, where I denotes the ith sample of the importance from the importance sampling estimate, and W denotes its weight. Okay. Now, I need to talk about something called the conditional particle filter. Algorithmically, the conditional particle filter is almost identical to the standard particle filter. And it's far easier for me to tell you in a picture and 2 lines what the standard particle filter does. So if you have never seen a conditional particle filter, you can understand this talk by just saying this person is talking about an algorithm called the conditional particle filter that has an algorithmic implementation very similar to a standard particle filter. If you know what a conditional particle filter is, then you might be annoyed by this slide. Okay? So let me give you a pictorial description of importance sampling estimate from x0 to little t, given y0 little t. And let me drop the weights. Let's just assume it's unweighted because of some magic at time 0 or time 1 that happened, that I could sample from the true guy exactly. Okay, but it'll be weighted, but let's just forget about the weights for starting. So here's a pictorial description of n samples from this density here until time t. So each trajectory here represents x0 to t. So there's n of them, so there's 1, 2, so on. You count them to n. And what you want to do in particle methods is that you want to extend this to an approximation of x0 to t plus 1 given y0 to t plus 1. And it's really just a 2-step algorithm. The first step, so let's just focus on a 2-step algorithm applied to every particle in the population. So let's just focus on one particle in the population. I erase everything else and look at one. The first step is just to extend the trajectory of this particle by sampling from the state transition density for the model. Okay. And the second step, so that's been extended for a trajectory of length t plus 1, little t plus 1 to little t plus 2. No? And the second step is to give this particle a weight according to how well it describes the observation at time t plus 1. Okay. And then you do this for everybody else. So everybody else has been extended and weighted. And you have this. And now what you do is that you make sure your weights normalize to 1. So I just called it capital W, departing slightly from the convention of capitals denote random variables and small denote instances of random variables. And then you carry on this process until the end of time, which in this case is time 14. And you may end up, and then, so there is a resampling step that happens because you want to stop the weights from degenerating over time. So you resample this population with replacement according to these weights. And so when you resample, you lose some of them, okay? And then you carry this process on until the final time, and that's each trajectory here represents your empirical approximation of this density you're interested in. Okay? Now, it is well known in particle filtering literature that this scheme can provide a good approximation of the density of interest, the law of x0 to t until time t plus 1. Okay. So the question is, why not use it as a replacement for the Gibbs sampler that we could not implement? So remember the Gibbs sampler in the example at the start of the lectures, start of the talk said that we wanted to advance a sample of the hidden states, and we needed to sample it from this, but we can't actually do it. So what we decided to do, what we could do instead is run a particle filter initialized at the parameter of interest, theta dash, and accepting the fact that particle filters do well at state estimation, we could just pick one of these guys at random, say, and that would be a replacement for the Gibbs step, okay, that we could not implement. Now, why not? Okay, why not? Well, one reason why not is because particle methods are used extensively in frequentist type techniques. So if you wanted to maximize the log likelihood of the data with respect to theta, you'd recognize this as being the EM algorithm. And in particle implementations of the EM algorithm, we routinely replace this expectation that should be computed with respect to the law of the hidden states given theta and y0 to t. So this should be a capital letter here, with a particle approximation. And nobody will quibble with you. Everybody is quite happy. So in that context, if you're quite happy, we could say, well, why not just repeat that idea within standard MCMC? Okay, and this is this is old understanding. It's been around for a long time. It's not dissimilar to things like particle learning and stuff like that. That's just sort of some kind of motivation to the origins of the conditional particle filter. As to the true origins of the inception of the method, well, Arno is here. We can ask him. He might tell you over beer. He hasn't told me. I've never asked. Okay, but I'm sure it's perhaps some sort of thinking like this, where it's just my spin on it. And we know from books by Pierre Del Morel. I feel it's slightly embarrassing to reference a book from 2004, but it's still and there's Eric's more recent book as well. But we know there are a lot of results concerning the quality of the particle approximation when you use a particle filter to sample from this. And basically, the take-home message that I just want to emphasize is that to get a good approximation, your number of particles must grow linearly with the length of the time series you are trying to sample. Okay, but then the problem being is in an MCMC context, if you were to do this, is that it suffers from bias, and you won't be targeting you will not be generating samples from the right target distribution, and bias can be an issue. We saw in the previous talk how bias is an issue for MCMC, even if it's trying to target the right distribution of interest. So fortunately, there's a bias-free meaning a mathematically correct way of using a particle filter within MCMC. And it's called the conditional particle filter, and it was published in a red paper in 2003 by Christoph, Arno, and Roman Holstein. Okay, in 2010 by Christoph, Arno, and Roman. Okay, and that's called the conditional particle filter. And this is what we're going to be talking about, the conditional particle filter. So algorithmically, I'm not going to tell you what the conditional particle filter is doing, because algorithmically it's doing something you have never seen this stuff. It's doing something very similar to this picture. Okay, so at least you have an idea of how it works algorithmically. And if you know this well, then we can then you can entirely ignore this slide. Okay, so the final step, the correct thing to do in the final step is to advance the state samples using a conditional particle filter. Now, a conditional particle filter algorithmically simulates a particle filter with n particles for t time steps, okay, as we did before, but with one tweak. And the tweak is that you keep one particle fixed at the sample you are trying to advance. So we're trying to advance x0 little t to x dash. We keep one particle fixed at that, okay, in a very simple way. Now, and then once we've generated a standard particle filter with this one particle fixed at the sample we're trying to advance, we then choose an output randomly according to its weight. And in effect, what the conditional particle filter is doing, it's defining a Markov kernel, okay? So we can think of the output of the conditional particle filter as a Markov kernel that is seeded at the sample you are trying to advance, okay? Obviously, it depends on the parameter theta, the current value of the parameter theta dash, and the number of particles you choose, you invest in this conditional particle filter, okay? What's remarkable about this conditional particle filter, without going into details about exactly, without giving you a description of its algorithm, it's remarkable that this conditional particle filter has the right invariant measure. Its invariant measure, this Markov kernel has as the target distribution is invariant measure, and this is true for any n greater than or equals to 2, okay? So given this is the case, we can really forget about theta now, okay? We can forget about inference of theta and just talk about how good the conditional particle filter is in sampling from this distribution, the distribution of the hidden states given the observation, and whatever the value of theta we're interested in, okay? So is it an effective sampler, and how should n grow with time, capital T? So this is something that people have sought to answer, and not me, and many people here as well. And algorithmically, this is going back again to 2013. I'm just peeling old simulations. Okay, it's just to reinforce the idea that the number of particles has to grow linearly with the length of the time series. If you invest 200 particles in a conditional particle filter to start a sample from this, you get sort of ACF plots for x0. Okay, not x at the final time point, x0, which is typically accepted as the one which is hardest to move. You have ACF plots that look like this. They decorrelate quite well. And if you know something about particle methods, you say, well, there's something called the residual particle. You can implement resampling with a residual resampling scheme, a systematic resampling scheme, and indeed you can do the same within the conditional particle filter. You get ACF plots that works much better. And then the final one is conditional particle filter with backward sampling, and that's something I'm going to talk more about. Okay, and that does even better still. So when we started off this work, we were, like most people, quite intrigued by why the conditional particle filter was working so well. And so we tried to prove something simple. We said, could we not prove that the Markov kernel defined by the conditional particle filter is ergodic? And so we decided to do so using a coupling construction. So we tried to couple, to prove to Markov kernel is uniformly ergodic. You can do this via coupling, and we thought we'll do a coupling construction because intuitively it made sense to us. Okay, not necessarily the most efficient way to prove this thing, but intuitively it made sense to us back in 2013. And basically, what you should do is that you can design a coupling. The outputs of two conditional particle filters, one started at x0 to capital T and one started at x tilde 0 to capital T. So these two conditional particle filtering Markov kernels can be coupled even when their inputs are different. And the coupling technique, the analysis is messy. Okay, if you look at the papers, the analysis is quite messy. And that doesn't mean it's clever, it's just messy. The analysis is messy, but algorithmically it's super simple. You can just say that, well, I'm going to implement two conditional particle filters with common random numbers. If you want to couple anything, the first idea that comes to mind is common random numbers. Okay, and so if you implement these two conditional particle filter with common random numbers and you make everything as common as you possibly can, then the outputs of them after one time step can be the same with some probability, okay, with some probability. And the whole idea is this probability significant? Is it close to 1, or is it something that we'll never see in any of our lifetimes? Okay, so algorithmically, let's call the coupled conditional particle filter as an algorithm that takes in the two different inputs we're at, and it gives you it gives you two outputs called capital X and capital X tilde, And marginally, these two outputs have the right distribution. So capital X is distributed from this guy, and capital X tilde is distributed from this guy. Okay, so I've told you nothing about how the coupled conditional particle filter works, other than the fact that if you implement a particle filter, two different particle filters, try to do so with common random numbers, and you'll end up with a coupled conditional particle filter. Okay, and what you can end up as well is that after each output of the coupled conditional particle filter, you have some probability of coupling. Okay. And once you couple, you stay coupled. So the idea is that the probability that the two outputs are not the same is less than some number epsilon. Okay, and so let's try to, and then it is established in this paper, in this early work here, that the coupling probability, which is 1 minus epsilon, can be made as close to 1 as possible by increasing the number of particles you invest in the conditional particle filter. Okay, so that's a good point. And if you have that result, then you peel off some very easy stuff, like you have uniform ergodicity of the kernel defined by the conditional particle filter. Now, but you see, this technique so there was no sort of rates here. We didn't know how epsilon scales properly with the number of particles. And so in a PhD student thesis of my student Bernd in 2014, some years back. It was never published, but we just archived it now, just the chapter that dealt with this issue I'm talking about. They were thinking that we were interested in is as follows. If the conditional particle filter is so similar to the standard particle filter, why can't we just reuse the techniques? We don't even ignoring couplings, because couplings is, it's very specific. Why can't we just reuse the techniques that Pierre Delmorel used in his book in 2004 and in the many papers on particle filtering from the earlier years? And indeed, you can use those techniques to prove uniform ergodicity of the conditional particle filter without knowing any more than, so you can do analysis of particle methods, you can prove uniform ergodicity of the conditional particle filter using very similar construction that PS uses in the analysis of particle methods, and you can prove a result like that says there is some time independent constant here, and the rate of contraction grows like capital T over little n to the power k. Okay, and then at this, earlier than this, and Christoph, Andrew, Anthony, and Matti, and also Randall, Frederick, and Eric came up with a result that proved the uniform ergodicity of the conditional particle filter by proving a minorization condition. And they said that the minorization condition is stable provided that the number of particles scale linearly with the length of the time series. So all this sort of stuff is consistent. In terms of, in my personal taste, in terms of the proof, I would say if you're not interested in coupling and you only know sort of particle methods, then probably these ideas are okay. But this, I think, is sort of, personally, I think it's probably nicer than these two. Okay. So the results say that the cost, how long do I have, Cody?
Half an hour plus.
Oh, wow, okay. So these results all say that the number of particles must increase linearly with capital T. So each time you run the conditional particle filter, you're simulating T particles forward for T time units. That's T squared per application, so that's expensive. And so we were wondering whether back in 2000 and I think 2014. Yeah, we were wondering whether we could try to come up with a technique, conditional particle filtering algorithm that was provably stable with a fixed number of particles. Okay, so could it work with a fixed number of particles, say n, that you would never have to increase regardless of the length of the time series you're interested in, and therefore you would cost n times t per application. And if you're trying to simulate time series of hundreds of thousands, this is a huge saving. Okay, so I should also mention that when I did, if you're not a stickler for sort of theoretical verification, you don't care about that, then there is, so Nick Whiteley in his 2010 discussion of the PMC-MC paper, the one that by the start of all of this, suggested the use of backward sampling that is well known within particle methods to enhance the performance of particle methods. This was published, I think, in 2004 with Arno, Simon Gottsill, and Mike West, and he suggested, Nick said, why not use backward sampling within within the conditional particle filter? And indeed, if you do that algorithmically, it makes a massive difference, and it does seem to work with a fixed number of particles irrespective of the length of the time series you are trying to simulate. Okay, but however highly successful it's been, there's been no real theoretical verification of this result. So we and other people, I'm sure, tried and had no success. So we came up with a very simple idea. It's so simple, it's mildly irritating. Okay, and the idea is as follows. If you want to sample from this, the law of the hidden state given all the observations, why not just think of a block Gibbs sampling? So here these boxes here with J1, J2 indicate a blocking of the hidden state. So I block them. A set of hidden states from time 0 to say, I don't know, L goes in J1, and then a set of hidden states goes in J2 and J3. And these blocks are overlapping because when you do blocking and MCMC, you need to overlap the blocks to have proper mixing of the blocks of the states at the boundary. Okay, and so when you sample, so you could sample the blocks sequentially, and when you sample a block Ji, say, if Ji runs from time R to S, then you need to advance the states in location R to S, given the state to the left of it, R minus 1, the state to the right of it, S plus 1, and the observations that pertain to the states R to S. This is because you're dealing hidden Markov model. That's why it collapses to this target distribution that you need to sample from. You want to advance block Ji, okay, while holding the remaining states unchanged. And then you cycle through the blocks in any order you want, randomly, sequentially, odd, even, whatever. Now, this in effect defines a Markov kernel that after one update, after one cycle of all the states, it defines a Markov kernel that goes let's just call it calligraphic P, because we want to not let it muck around with the kernels that we have introduced thus far. And if you, I mean, this is uninteresting. I mean, it just says that if you're going to cycle through blocks in an odd even way, you get a composition of the stuff. It's not interesting for what I'm going to say now. Okay, so the question is, our thinking, why I said this was very, very simple is because the problem we ran in before with all the results on the conditional particle filter and its rate of convergence to the target distribution, it suffered because you were trying to use the conditional particle filter to sample, if you want to use it to sample time series of longer and longer lengths, you had to invest more and more particles in it. So somehow, if you were to curtail the length of the target distribution, then you would never have to grow the number of particles. So that was the thinking behind why blocking and conditional particle filter might give you a sampler that works for a fixed number of particles. And indeed is the case. So to establish this result, you need to do two minor things, which with a lot of messy working. The first is to say, if you had an ideal block Gibbs sampler for the state process, how quickly does it converge to the target distribution, which is the law of the hidden states given the observation, and it has this sort of convergence behavior. It doesn't care about the length of, so it contracts at rate lambda to the power k. Lambda is some number less than 1. Lambda doesn't care about the length of the time series. The contraction, though, has a constant that is t plus 1, grows linearly with the length of the time series. Okay, but the most important thing is lambda is independent of the length of time series. And so there's some tuning to be done here. You have to somehow choose the length of the blocks. You have to choose the amount of overlap. And once you've done this, for the specific model you're interested in, you don't have to play with the length of the blocks and the overlaps anymore. It'll work for any length of time series. Okay. So, and obviously, if you overlap the blocks more, the rate of contraction quickens. Okay, and so the idea now is very simple. This is your ideal block Gibbs sampler. Now you can use, when you try to update each block, you use the conditional particle filter. So here is the conditional particle filter kernel to update each blocks. So what you can end up with a result that says that if you block the states and you apply conditional particle filtering to each block, and you do this over and over again after sweeping through all the states, you'll end up with a behavior very similar to what we had before, a contraction rate that is independent of the length of the time series, a scalar that grows linearly with time, and this contraction rate lambda, which is now subscript n because it depends on how many particles you invest in the conditional block particle filter. And our best attempt at quantifying this rate lambda n is something like that. It says that you lose the original contraction rate by square root, where you had lambda before, you become square root lambda. You got some constant that's small, I think it's 3 or 4. you got multiplied with the maximum length of the block size. So I told you your block sizes don't have to grow with the length of the time series. You just have to, you can have a fixed block size and the number n 1 over n, where n is the number of particles you invest in sampling each block. Okay, so this is the rate. Okay, so I'm going to return to the coupled conditional particle filter. Okay, and I'm just going to remind you what we did. And the reason is because very recently it's been used in an algorithmic technique, in an algorithmic setting for debiasing MCMC by Pierre Jacob, Thomas Schon, and Frederick Linston. Okay, so where it's set as purely a proof technique in 2013, it has a practical use now. Okay, so just remind yourself. Just to remind you that the coupling of the conditional particle filter is basically nothing more than an algorithm that simulates two conditional particle filters with common random numbers. We denote it by CCPF, coupled conditional particle filter. It takes the two inputs, the different inputs of the chains you're trying to couple, and it produces outputs. They're marginally, they have the right distribution, they follow their appropriate Markov kernels, and the probability of coupling is not zero. Okay? It's something that can be controlled by increasing the length, increasing n, capital N, the amount of effort you use to simulate the conditional particle filter, or how many particles are in there. Okay, and so this is the algorithm for unbiased simulation. Okay, I don't want to repeat what was said already, but the most important thing is that if we want to estimate, so I don't know why, I've called it Z here, but if we want to estimate the expected value of some state, sorry, of some function with respect to the hidden states, expected value computed with respect to the conditional distribution of the hidden states given all the observations. We can estimate it unbiasedly using this algorithm. It has a specific initialization, okay, which we went through, which has gone through before. The specific initialization is unimportant for us because it serves no difficulty here. The most important thing is that you need a way of coupling the two conditional particle filtering Markov kernels, and you can use the coupling technique that was devised in that paper with Nicola in 2013, and the expected value of the test function of interest is unbiasedly estimated by evaluating the outputs of in some sense, without being perfectly accurate, in some sense, just evaluating the outputs of, the difference in the outputs of the test functions along the two trajectories you're trying to couple. Okay, that's all you do. So this algorithm that works doesn't care about conditional particle filtering, that works for any Markov kernel, was proposed in Glynn and Ree in 2014, and it is Pierre Jacob, Frederick Linston, and Tom Schon in 2017 that used the CCPF within Glynn and Ree scheme, and they produced some quite remarkable results concerning unbiased estimation for time series using the conditional particle filter. And that's what got us interested last year when we all met at the Isaac Newton Institute in a program that was run there on intractable inference. Okay, so coupling for unbiased estimation, if you ignore the specific way they are initialized, works. Okay, you need the kernels that you're trying to couple to be ergodic, and I need to quantify the coupling time because really the algorithm runs for unbiased estimation. You run this coupled conditional particle filter until the two outputs meet, and then you stop and you produce this as your output, Z, for the unbiased estimation of this. So we need to quantify this coupling time. When does it happen? Okay. So recently, under very weak assumptions, what we have been able to do is to show that the tail behavior of this coupling time, okay, follows this distribution. So the probability that the time exceeds capital little k dies as some constant c over c plus n, where n is a number of particles. So this rate is significant to so this rate might be meaningful to people who know sort of the analysis of the minorization of the CPF kernel. Okay, but unfortunately, the constant c is not stable with the length of the time series you're trying to simulate. Okay, and our best attempt at stabilizing the constant c with respect to the length of the time series is to say that under stronger assumptions, the coupling time is stable provided the number of particles increase double with the length. I mean, they double with every addition of an observation. So they grow like 2 to the power t. This is our best attempt. So this vanilla coupling algorithm was used within the paper of within this paper of Jacob, Linston, and Schoen, which I understand has just been accepted in JASA. And it produced some quite remarkable results. Okay, regardless of, in effect, the best theoretical verification we can come up with says that the number of particles has to grow quite quickly with the length of the time series to provably show that the coupling time is stable. Okay. So the problem with this coupled particle filter is that we demand a lot from it. Okay, and what do I mean by that? So the problem here is that we rely on one-shot coupling. So every time I push a trajectory through the coupled conditional particle filter, we ask it, have you coupled everything yet? Is everything coupled? Is the entire length of the trajectory from time 0 to t coupled with the other chain from time 0 to t? And that's a lot. And because we ask this, and that's why we end up with quite bad rates. Okay? So we want a version of a coupled conditional particle filter that again works with a finite number of particles irrespective of the length of the time series. Okay, because we can't increase particles as we had in the result before. Okay, and I'm just having a feeling I forgot to mention something, but I can't remember what it is, so I'll move on. Okay, and the idea we had is really to try to couple the trajectories progressively. So we are trying to couple 2 trajectories of the time series of length capital T. So why not keep track of how much of them have coupled? So we scan the 2 trajectories from time 0 to little t, and we increase little t from time 0 to capital T. Okay, and we check how much of that has coupled. Okay, and that we define that to be the coupling boundary. We call it kappa n. If we can, so the idea is as follows: if you tweak the coupled conditional particle filter with just a backward sampling step, as proposed in Nick's discussion of the red paper. So you got to design a coupling of the conditional particle filter with backward sampling. Your coupling boundary, we can show that the coupling boundary actually drifts to the right. Okay, so you don't have this very difficult situation you're in where you demand coupling of the entire trajectory in one shot. You let the coupling boundary build up. These 2 trajectories couple sequentially. Okay, they progressively. Every application is make of the coupled particle filter or conditional particle filter makes some progress towards complete coupling of the 2 trajectories. So in the same paper with Anthony and Mati, we were able to characterize the distribution of the coupling time, okay? And its tail behavior behaves like this. It decays geometrically, okay? And the point to be made here, how these results should be read is that irrespective of the length of the time series you're trying to couple, provided your particle number n is large enough, so we don't care about the length of the time series, provided the particle number n is large enough, there are some constants alpha and beta, where beta is less than 1, okay, such that the coupling time, the tails of the coupling time decay as follows. We understand this by just saying once you have simulated the coupled conditional particle filter with backward sampling steps, for length of time t, for the length of the time series you want to couple, then you start getting very rapid progress towards coupling. That's how you can understand this result. There are a few corollaries of this very simple statement here. One of which is that you have some strong guarantees that the coupling time, in fact, you can say that probably the coupling time exceeds some constant times capital T goes to 0 as capital T tends to infinity. So you got strong guarantees that you will couple in roughly time steps which are linear in the length of the time series you're trying to simulate from. Okay, and another corollary of this result is a verification of a well-known algorithmic fact that if you implement particle Gibbs or the conditional particle filter with the backward sampling as Nick suggested, then you can actually prove that this implementation is stable with a fixed number of particles. A corollary of the result states that the backward particle filter, the conditional particle filter with backward sampling steps is uniformly ergodic, and it decays to its target distribution in a rate which is stable in the length of the time series once your particle number is large enough. Okay? So again, you can read this result as saying you start contracting very rapidly once you have iterated the conditional particle filter with backward sampling steps for at least the length of the time series. Then you have very quick progress towards to contraction towards the target distribution of interest. Okay? Now all these results, again, I've said nothing about how we prove them, or I've given no insight about how these results are proved, just a statement of the fact. But the proofs that we come up with actually need a cutoff of a number of particles, before which we can't do anything, after which then we start seeing rapid progress towards coupling, before which we see nothing at all. Okay? And so we were concerned that maybe this is is this really an artifact of how poor the proofs are, or is it really something you see in practice? So there are some numerical results. This paper hasn't been submitted yet, but we are tightening it up at the moment with some numerical studies. So this is some results I can show you. So what I'm going to look at is we are trying to couple two time series of length 1000. Okay, the length of the time series here is 999, 0 to 999, so that's 1000. And this is how quickly coupling happens, cost of achieving coupling, how it changes with the number of particles. If your particle number is high, say 256, to couple a time series of length 1000, then you make very rapid progress towards coupling, okay, as a function of the work per iteration. Or the total work per iteration. Once the particle number starts decreasing to 128, then you get the green one. You couple later. The rusty colored 164, you don't couple. You don't seem to couple, but there seems to be some drift. But the thing is that all the progress you have made is completely erased. Look at that. Okay, so and the lower number of particles, 32, there is no progress towards coupling. There's some drift, but again, all the progress can be completely erased. So this is not absolute guarantees that this threshold behavior is correct, that you have to have a certain number of particles, minimum certain number of particles before you start seeing coupling, but it is some indication of this sort of behavior going on. Okay, it's something we'll seek to verify more in numerical examples. So this shows some sort of gives some verification of the cutoff behavior for coupling of conditional particle filter implemented with backward sampling steps. Okay, and also what's interesting is there seems to be an optimal number of particles. Okay, if you optimize the number of particles with respect to the work you're going to do, so what we have here is as we change the length of the time series, capital T, from 50 to 100 to 150 to 100 to 50. We try to work out how quickly coupling happens as a function of the number of n, okay, number of particles. I mean, the graph here is not labeled, okay, and it's a poor show on my part. I apologize for that. But in essence, what you can see is that this is n equals to 32, this box plot. And you can see that 32 particles seem to be the right number regardless of the length of the time series once you have fixed that particular hidden Markov model you're interested in. Okay, you change the hidden Markov model, the best number of particles will change. But for this example, 32 seems to be the right number regardless of the length of the time series. Okay, and that optimizes coupling time with respect to cost of achieving coupling. Okay, so there are few more results we are trying to run now to show how this technique with coupling of conditional particle filters with backward steps outperforms just the vanilla coupling of conditional particle filters without the backward steps. Okay, we're trying to come up with some numerical results that show that categorically. We have got some preliminary stuff that I haven't included, but I will leave it at that. So the take-home message is that in terms of an algorithm, the coupled conditional particle filter with backward steps is easy to implement, and it seems to be an effective algorithm for unbiased estimation, as Jeremy talked about in the context of what Jeremy talked about for time series, for inference in time series models. Okay, and that's the take-home message, and these are some of the references concerning the work I mentioned. Okay, so I'll end it there. Thank you so much. No, I didn't mention it. I didn't mention it because it's the usual set of assumptions everybody makes when they prove stability of particle filters.
Like the decision density is not out until.
Yeah, it's the strong mixing assumptions. Yeah.
But is it easy to get to use something? For example, if you have like SDE, and you think about like how does SDE propagate through time?
Yeah.
Small time interval, when it's not, you don't have like a lower bound because
Yeah. So, yeah, just leaving aside even that example, basically, is it easy to generalize to cases where people have looked at weakening the assumptions for stability of particle methods? I don't know. I haven't looked at that at all. Yeah, and I'm not sure I'm that motivated. Not that it's unimportant. Okay.
Let's break for coffee and we'll